And in the not distant future, we will be rewriting the code of our lives. And on top of that, we know that technology doesn't slow. As a matter of fact, it speeds up. And that every time we have a new technology like CRISPR gene editing, it seems really cool at the time, just like we all thought the Sony Walkman was really cool at the time. But technology has a way of moving on an exponential curve. And so what are these three phases of change that are already taking place? The first is something we're all familiar with, IVF, in vitro fertilization. Everybody knows about IVF. It's been around for almost exactly 40 years. As a matter of fact, on July 25th is the 40th birthday of Louise Brown, who was the first IVF, what they then called test tube baby. And so with IVF, though, there's a second process called pre-implantation genetic diagnosis, PGD, or PGS, genetic screening. And what that is during IVF, you extract eggs from the woman, and on average, woman has about 15 eggs extracted during IVF. And then you fertilize those eggs with the male sperm, and there's hundreds of millions of male sperm in the average ejaculation, so sperm is easy to come by, as Martine mentioned this morning. And then you grow these eggs for about 5 days, 5 to 7 days, and you extract 5 or so cells from each of those. You sequence those cells, and then you get a lot of information about each of those 15 or 10 or whatever the number is pre-implanted embryos. And so what can you tell about those pre-implanted embryos? Well, you can tell anything that you can tell from genome sequencing. And what can you learn from genome sequencing? Well, right now, it's single gene mutation diseases are the primary focus, and a few relatively genetically simple traits like hair color and eye color. But we are moving towards a stage where we are going to know more and more about what our genes do. And the reason for that is that, having nothing to do with the future of reproduction, we're moving towards a world of precision medicine. And that means rather than having medicine based on generalities and averages, your healthcare will be based on you personally. And so your sequenced genome will be the foundation of your electronic medical record. And because of that, we will ultimately have billions of people whose genomes will be sequenced and electronically available, and their life records will also be digitized and available. And by comparing the two, we're going to be able to learn a lot more, not just about single gene mutation diseases, but about extremely complex, mostly or even partly genetic traits like height, like intelligence, like personality style. And then, using this exact same process, but adding another technology that already exists, called the process for creating induced pluripotent stem cells, and Shinya Yamanaka won a Nobel Prize for this discovery in 2012, we're going to be able to turn any adult cell, a specialized cell, into a stem cell, and then into another type of cell. So the way this would work is you take a blood sample or a skin graft, you turn those skin cells into stem cells into egg precursor cells, and those egg precursor cells into eggs. Now, rather than having 10 or 15 eggs, you have 100 or you have 1,000. You fertilize all of those eggs, and now the range of what you're choosing, let's say it's 1,000. And so for whatever you are selecting for, the range, whether it's IQ or height, you'll have a much greater range if you're choosing from 1,000 and then if you're choosing from 10. And then what you can do is have these early stage pre-implanted embryos, and again, I'm aware of all the ethical issues, and I'm aware that we're in Germany talking about these issues, so we'll talk about this in a moment. But then what you can, or I should say could do, is take these early stage pre-implanted embryos, maybe the one you chose of 1,000, and you could do that same process with their cells, so generate eggs from a pre-implanted embryo, or sperm from another pre-implanted embryo, and those 5 to 7 day old embryos could then have a child. And so what that means is right now it takes a little under 30 years to pass a human generation, but we could be passing human generations in 6 months. And so that means 60 generations in the space of one. And what does that mean? Our ancestors, only using selective breeding, took the wild chicken that lays 1 egg a month and turned it into the domestic chicken that lays 1 egg a day. So we can go a long way with this type of embryo selection. And then we haven't even spoken yet about gene editing and CRISPR. And gene editing has been around for a while, but what CRISPR does is make editing any genome, including our genome, by far faster, cheaper, and easier than ever before. People use the analogy of editing a Microsoft Word document. It's probably harder than that, but the rate of improvement is so quick that we are moving in that direction. And it won't be that we're going to be creating whole humans from scratch, but already barriers are falling on gene editing, pre-implanted embryos in the animal kingdom, and very soon it will start with humans to eliminate deadly single gene mutation diseases, and sickle cell disease will probably be the first. So this is where we are going.